Yeah, I can say.
Okay, great. Let me go ahead and get started. So, hi, I'm Sam. I'm the co-founder and CTO of Miston Labs and the creator of Move. And I'm super happy to be here today to talk to this enormous Move community. It's really humbling to see from a small project we started way back in 2018 to have grown a large group of Move core contributors and a large audience of Move programmers. Here in the US and Europe and in China, around the world. It's just really a wonderful thing to see. So I'm happy to be here and to talk to you all about a little bit about Move and particularly about what we're doing with Move and the Sui network. So my talk today is going to be divided into four different parts. I'm going to start off with just a little bit of background motivation for Move as a whole. I think it's a great opportunity while addressing this broad audience just to say why I think Move needs to exist and the key problems that I think it's solving. After that, I'll go into an overview of Sui Move, where I talk about how we combine the ideas of the core Move language with the object-centric data model that we're using in Sui. And then I'll walk through a short example in Sui Move, just so you get more of a sort of hands-on idea of how Move programmers end up working in Sui. And then I'll conclude by talking about how the other side of the marriage of Move into Sui works. What are the features of Move that Sui is leveraging to do some of the interesting things it's doing with respect to scalability and decentralization. So to start off, I think the key reason why Move exists is this problem of smart contract safety. I'd go so far as to say that smart contract safety is an existential threat to broader crypto adoption. If you take a look at how frequently there are really large hacks, it's sort of these hacks that are worth tens of millions or hundreds of millions of dollars happen more or less on a weekly cadence. And these hacks happen in spite of the fact that the early developers of smart contracts are folks who really understand underlying blockchains. They're really security sensitive. They're really dedicated to their craft. I think basically they're the best group of developers that the space can hope for. I think if the space is going to grow, newer developers will care less about understanding the underlying blockchain, or will be more interested just in building products and doing things on top and just basically trying to get a job done. And so if the best set of developers we can expect have this sort of unacceptable security track record, that means that there's no way the space is going to grow in a sustainable way. Either it just won't grow at all because people will be too afraid to enter it because of smart contract safety, or when we do bring in new developers, these hacks will get worse. The problems will become more frequent, and things just won't be safe enough for crypto to have the potential that it could have. So my thesis for this is that if we really want the space to grow, the only way to do that in a sustainable fashion is to provide languages that are safer and tooling that's more advanced to help developers actually be able to write safe code that manages real money in the presence of adversaries. This is a super hard problem, and we need to give developers all the help that they can get. I really believe that safer languages and advanced testing and verification tools are the only sustainable way to grow the dev community. And I think Move is the best candidate out there for this particular task. So I think this audience is familiar with it, but let's spend one slide talking about basically how Move is solving this problem, that it's not just talk. So the Move design is everything in the Move design is optimized around safety and predictability. So first and foremost, there's no dynamic dispatch. Every time you call a function, you know exactly what code it's going to invoke in advance. An attacker can never inject some code that surprises you. And this in turn implies that there's no reentrancy, which is a major source of vulnerabilities in Ethereum and other platforms. Basically, making the code all static just makes it much, much easier to reason about. We have aliasing and we have mutability, but we don't allow them to mix. Move has a borrow checker that's much like the Rust borrow checker. So as a programmer, you can have the convenience of distinguishing between values and references, but you don't have to worry about creating dangling references or memory safety issues that wouldn't be acceptable in a blockchain setting. You have the key properties that you care about: type safety, memory safety, and so-called resource safety. These are all enforced by the bytecode verifier. So these aren't just protections that exist for you as a programmer in the Move source language, but they also exist when these are also enforced even on attacker code, because the bytecode verifier runs on your code before it's allowed to be published on chain. Move has really strong isolation features, or so-called robust safety by default. So it's easy for programmers to write code that enforces invariance on their types, but then the types can flow into untrusted code and continue to maintain their integrity, which allows you to have a nice mix of flexibility, but also safety in the terms of these types. And then this is sort of a small thing, but I think it matters a lot or it's a big problem in the Ethereum world, any kind of operation that's mathematically ill-defined, like integer overflow or division by zero or anything like that, aborts instead of doing the ill-defined thing. If you're familiar with Solidity, you might say move has safe math by default. And then finally, and we'll hear a lot more about this later from Mung and other folks in the program, Move has been co-developed since the beginning with the Move prover formal verification tool. Move can take a lot of things off the table for the programmer in terms of safety by default, but at the end of the day, you're always going to have some safety properties that are inherently application specific, and the prover gives you a way to specify those things and then prove that they hold for all possible program executions, all possible function calls, no matter what attackers can do, which is the strongest form of correctness that we know how to achieve. So I think the second important problem that Move is solving is that it's platform agnostic. And so if we look at existing smart contract languages today, the sort of status quo is that there's about one language per blockchain. And this isn't a good pattern for programming languages. Programming languages do best when they have when they can be used as broadly as possible. They have a community, they are used on many different platforms, many applications, many websites. If you only have one language per blockchain, that's not a good recipe for building a large community or investing in tooling or even having developers who are motivated to learn this skill because of all the different learn this language because of all the different opportunities, both in terms of jobs and apps and things like that it will buy them. So another problem is that existing smart contract languages, they tend to hard code key factors like the account format, the transaction format, the serialization format, the cryptography that's used, even the consensus in some cases. And so that means if you're launching a new blockchain platform, but you don't want to launch a new language, you're sort of in a tough spot. You can use, say, the EVM, or you can use a different blockchain language, but your platform will have to inherit the design decisions that the previous platform designer made, and some of those may be leading to limitations that you would like to work around in your new blockchain. And so we really think crypto is very early. The blockchains are very early. No one's settled on the best design yet. And so platform designers really need as much leeway as they can to experiment and to try out new things and to try to make things more user-friendly, to make them more scalable. But we don't want them to have to invent a new language every time they want to do that. And so what we've done is we've tried as hard as possible to make Move agnostic to all of the factors above and to anything really blockchain-y specific. The core language is super minimal and it doesn't have anything that refers to a particular blockchain. So this allows platform designers to experiment with different choices for all of the things above, but we can still build a large community of programmers that can reuse their expertise, the tooling, like the VM, the bytecode verifier, the compiler, all this, the prover, all this stuff, and even some libraries across platforms. And so we're starting to see this vision emerging. Move is used in 4 blockchains that are all very different under the hood. We have Sui, we have Aptos, who just launched very recently, and then Starcoin, the OG Move platform, and then we have OL, who launched in the fall of last year. In addition, there's lots of interest in Move from existing chains who want to add Move as a second language, like Solana or ETH as a rollup, and also emerging chains like Celestia that are sort of language agnostic and want to incorporate Move as one of many options. So the vision we have for Move in terms of platform agnosticism is really that it's the WASM of Web3. Every time you have a blockchain, every time you're programming with assets, every time you're writing smart contracts, you should be doing this with Move, and we'll build a beautiful community with folks that can take this expertise and use it wherever they want. And so to talk a little bit about how Move actually allows this, how platform designers can customize Move, the structure of a Move integration on a blockchain is typically something like this. So you have a transaction. This is blockchain specific. The platform designer can pick whatever structure they want for that. Move doesn't impose any sort of problems, any sort of constraints there. Then you have the framework modules, which define the core logic of the blockchain, coins, accounts, cryptography, any of that stuff. These are usually the modules that exist at Genesis, and there too, Move doesn't require anything from you. The platform designer can pick whatever they want. And then finally, there's persistent storage. Maybe you're using RocksDB, maybe you're using some other database, maybe you have a different schema. That Move also doesn't care about that. It has a very thin API with the external storage layer. It basically just needs to be a key value store. And so the platform designer can pick both whatever schema and whatever actual data store they want there. In addition, the platform designer can extend the underlying Move bytecode verifier if they want to put more restrictions on the Move language. And so basically the idea here is that everything that's blockchain specific that you might want to experiment with as a platform designer, Move will let you do that and still use the tooling and the language and build the community. And this also makes the governance for the core language less controversial because, say Sui and Starcoin don't have to agree on what the cost of that gas cost of the add instruction could be. We can each choose that in our own platform. We don't have to decide what the framework modules can be. We can each make our own choices. We have a lot of leeway to experiment while still using the same core language and benefiting from everyone's shared contributions to that. So that's the high level picture of Move. The rest of the talk is about Move on Sui, which is one particular instantiation of these choices of transactions and framework modules and persistent storage that we're trying out in Sui that we think has some interesting properties. So let's go into that part. So I'm going to start with a motivating example that's some code in DM style Move that I think is the sort of thing that you need to write pretty frequently, but isn't necessarily the best code or the most fun code to write as a developer. And so this is just something where I'm implementing NFT and I'd like to transfer it, but I want to have a lockup period, maybe to make sure that when the original owner gets the NFT, they can't just flip it right away. They have to wait a little bit to sell it. And so I don't want you to look too closely at the DM style Move code here. I'm sure everyone who's written DM style Move code has written something like this before. The main thing I want to call out is the things on the right-hand side, these 5 different steps that the programmer has to go through. So the first thing they would have to do is they define a wrapper around a table that can hold multiple NFTs of the same type. And the reason they would have to do this is that in DM style Move, the global storage is keyed by address and type name, so you can't have multiple objects of the same type under the same address. And so if you want to do that, you have to work around this by having a little wrapper of a store that is keyed by some ID thing, and then you can have as many cool assets as you want under the single address. And then the next thing you have to do is you have to write some function that lets the recipient opt in to receiving assets of type cool assets. So here, you create a cool asset holder and you move it under the recipient's account. And the reason you need to do this is that the recipient can't just say, hey, let anyone send me any object. Move to is restricted to signers, so you have to opt in to receiving this thing. Then there's the actual transfer function itself. You start off by grabbing the cool asset store under the sender, and then you look up the ID of this token inside of it, and you make sure everything exists. And then finally, down here, you actually have the asset in hand. Then in step 4, you write the actual meaningful part of the logic here. You look at what the time is, you make sure that 30 days have elapsed since the creation date, and you abort if you have not. And then finally, if the check passes, you sort of do the mirror image of what the first part was. You look up the asset store of the recipient, you get a pointer to its assets, you insert the asset into the table, and then you're done. And so this ends up being a lot of code for something that's fairly straightforward. Really the only meaningful part of the logic here is checking this lockup period, but we have to write all of this code to be grabbing the wrapper and then getting the asset out of it, putting it back in, and all this sort of stuff. So what is it exactly that makes this code so long and indirect? And so when I look at this, what I think is that entry functions and the global storage API and DM style Move are just not very asset centric. You can't pass an object directly as an input to the transaction. And then the global storage API forces this indirection layer of a wraparound table rather than a direct lookup of the recipient object or address. And so I think what the programmer would really like to be able to do in this code is say, hey, I want to send a transaction that passes cool asset with the ID I care about directly into the cool transfer function. I want to check the lockup period, and then I just want to transfer the cool asset directly to the recipient. I don't want to deal with these wrappers. And so in Sui Move, this is what the code will actually end up looking exactly like this. You'll say entry fund cool transfer. You've got your asset here. You've got the recipient, which is an object that you can pass directly into the entry function. You've got the recipient address, and then you've got this transaction context thing that has the time and various other stuff. Then we do the actual check for the expiration. We look at what the current epoch is, which is basically a day, and then we make sure that 30 days have elapsed since we initially created the thing, and we abort otherwise. And then if that check passes, Sui Move has this built-in function called transfer that just lets you take any object and put it under someone else's address. And so this ends up being a lot shorter than the equivalent code in DM style move and a lot more of a direct expression of the programmer's intent. So what makes this possible? I showed you the code, but let me explain what Sui is doing under the hood that allows you to do it. And so the key thing here is that Sui Move is organized around objects. Every object in the system has a stable, globally unique ID, which is different than in DM style move, where objects don't have IDs, they're identified by their location. This is the object that's under this address of this type that's under this address. That's the only way to really identify an object. And here, unlike that thing, which is the location-based identifier, objects retain their identity as they move around a system. If my NFT has ID A when it's under my address, it'll still have ID A when it's under Joel Starr's address. Each object also has a version that increases each time the object is used. And so this lets you track how many times the object has been touched and sort of have a vocabulary for talking about where it's been at different points in time. And then finally, all objects have ownership metadata. And so there's a couple of different ownership modes. An object can be owned by an address A, and the policy associated with that is that only a transaction that's signed by the key behind address A can use the object O. An object can be owned by another object P, which means that a transaction that includes P as an input can look up O at runtime if it wants to, like the P might be a table and O might be an entry in the table, that sort of thing. Then there's a notion of a shared object, which is sort of like an Ethereum smart contract where anyone is allowed to use that object. It doesn't have an owner like an NFT or a coin would. So like an auction or a crowdfunding or an escrow, this sort of thing would be a shared object. And then there are also shared immutable objects where anyone can read them, but no one can write them. And the way this fits into the global storage is that it's object-centric instead of being address-centric. The structure of the global storage is a map from object IDs to objects, as opposed to DM-style move, where we have a map from this address type name pair to objects. And so in Sui Move, you can't use move from or borrow global or any of the other global storage operations that are familiar in DM-style move. Instead, what happens is, as we saw on a couple slides ago, you pass all the objects you want to use as transaction inputs, or you read them from other transaction inputs. The language is pure in this way. And because the object ownership info is in the metadata, an address can hold an arbitrary number of objects of a given type instead of just one, which is the restriction that this type name bit of the DM style move storage enforces. So Sui transactions are also object-centric. Every transaction declares, hey, here are the objects I'm going to use. Objects are identified by their ID and their version, or just the ID for shared objects. And then the effects of a transaction can also be expressed in terms of objects. All a transaction does is it reads objects, it can write them, it might create them, it might delete them or transfer them. And then, of course, it can also emit events, which is the only non-object thing that it does. And the way a transaction specifies the function to call is every transaction contains a move entry function, and this function can directly take objects as input. And so because of this, the function's type signature sort of conveys object permissions in this interesting way. If I have an entry function that's called f, and then it takes one argument that's a t, another argument that's an ampersand mute t, and another argument that's an ampersand t, what this function is saying is, I would like the permission to transfer, delete, read, or write t. I want to be able to do anything to it. For ampersand mute t, I'm asking for the permission to read it and to write it, but not to transfer it. And for ampersand t, I'm only asking for the permission to read it. So let me walk through an example of how exactly this works and how Sui is able to let you pass objects as top-level inputs. So on the left side here, we have a transaction. It has a sender address. It's a move call transaction. And this move call transaction specifies the ID of a package that's going to be called. A package is just another kind of object in Sui. It specifies a name of a function inside that package that the transaction is going to call. And then it specifies a couple of arguments here. I've got the object ID 0xb and the version 3, and then I've got the pure value false. And then on the right side, we've got the global storage. The global storage has two objects in it. There's this object 0xa that has a module inside of it that declares an entry function. The entry function wants a bool and an object type, and then this tx context thing. the other thing in global storage is this object OXB. It's got an object ID that, of course, matches it's the key in the global storage table. It has an owner field that tells who its owner is. This is owned by OX1. It has a version, which is 3. And then it has a move type, which is myobj. And then it has data, which are just the BCS bytes of the object itself. And so what the Sui runtime is going to do is first it'll look at the arguments and see which ones are object IDs, and it'll resolve each of those IDs to an object. So here it'll see OXB and it'll say, all right, let me go grab the object associated with OXB from the storage, make sure that it exists. And similar for the package ID and function name, it'll say, okay, go grab me the object with ID OXA, look at it and make sure that it's a package, and then find me this function MF inside the package. The second thing that it does is it'll check the ownership of the object. So here it'll look at the owner field, it'll make sure that, okay, the owner is OX1, that's also the sender of the transaction. So this is a valid transaction, it's safe for that transaction to use these objects. And this is very nice because the programmer doesn't have to check this ownership information as they would in other languages or in DM-style move. This is just checked for you by the Sui runtime. And then finally, it checks the object types against the entry function signature. Here it'll say, okay, the type of this object is a myobj, and this function wants a myobj. So that's all good. I'm totally okay to plug it in here. Finally, it'll just go ahead and call the function with the concrete object data and the pure args. Basically, it takes the data, it binds it to the O field, it takes false and binds it to B, and then it generates a TX context from the sender and some other stuff like the current epoch that's in the transaction that I haven't shown here. And then it just calls the function and applies the effects. So we've walked through how this works. And so basically this now, I think, can help explain how this Sui move code is able to be so much shorter than the equivalent DM style move code. Basically, there's a lot of steps that are happening in the DM style move code that are just either not needed because of Sui's design or taken care of by the Sui runtime. So one step in the older code is that you needed a table of, you needed this wrapper around table ID cool asset to hold multiple entities of the same type. But in Sui, you don't need that because an address can hold an arbitrary number of objects of the same type. When I do transfer asset recipient, that'll just change the owner metadata to be recipient, and that's all we have to worry about. Another thing is that the recipient doesn't have to opt in to receiving cool assets by publishing a wrapper type. This transfer will work regardless of whether this recipient address has ever sent a transaction or created an account or done anything like that. It can be done to just any address, regardless. There's no notion of address existence or anything like that. And then finally, there's a lot of code in the original DM style move where we were looking up the cool asset and making sure that the NFT with the appropriate ID exists and removing it from the sender address. And we don't have to do any of this stuff because the Sui runtime is just doing it for us. At the time we start writing the code, the cool asset is just sitting there in a parameter and we can just do whatever we want with it. So we think this is quite nice in terms of taking a lot of boilerplate that comes up in writing ordinary move and really just using some aspects of Sui to get rid of a lot of it. So that's an overview of basically how the data model of Sui style move is different and how it fits in with this object-centric transaction data model. Let me now go a little bit deeper into a specific example to show you some other features of Sui move. And so the example I'm going to use is a crowdfunding contract. This is it's not exactly rocket science, but this is a very classic smart contract use case that I think is just everyone knows what it does, so you can look at it in different languages and sort of understand like what you should be looking for and focus on the minutia that the language is going to expose. And so here we have this fund. It's got an ID. This is the UID. That's the type of the globally unique ID that every object has to have. There's the target, the number that we must hit in order for the crowdfunding to be declared a success. And then there's this funds variable that stores the coins that we're going to deposit. And then what we do is there's this function called init. So this is a special functions that are called init, and there are these special module initializers. They're run exactly once when you publish the module for the first time. So this is a very convenient way to create singleton objects, which there's not necessarily a very convenient way to do in the core move language. So this init function takes a transaction context as input, and then it calls this function. It creates a crowdfunding object. It derives an ID for that from the transaction context. It sets a target of 100, and then it creates an empty coin to hold the funds to be donated. Finally, it calls transfer share object, which is this special function in the Sui framework that just says, hey, take this object that I've created and set its ownership metadata to be shared so that anyone can interact with it. So this is basically creating this singleton crowdfunding object that now anyone can go and, as we'll see, make donations to, or sorry, I'm having some issue with Vuv. Can everyone hear me still? There's an error message that popped up, but I couldn't see what it was.
On the top of the screen.
Yeah, are we okay? Everyone can see my crowdfunding slide?
Yeah.
Okay, sorry, I'll continue. I don't know what happened there. Okay, so this was how you initialize the crowdfunding object. And so now let's look at what donate would look like. So I write a function called donate, and all I do is I take the fund that I want to work with directly as an input. Here, I don't take ownership of it. I just say, hey, I want permission to mutate it. I take the coin that's going to be donated. This is also an object that I don't have to look up. I just pass it in as an argument, and then I take a transaction context. I join the coin that I got in with the raised field of fund that just basically smashes the coin into raised. And then I check if the total value that's been raised so far is greater than the target. I do something, I emit an event, I send everyone a promotional NFT, I do goods, whatever the crowdfunding is doing. So this is just another illustration of passing these objects directly. And now what I want to show you is how object upgrades work in Sui. Like, let's say we look at this code and we decide, oh, I've actually made a mistake here. There should be an expiration for this funding, for this crowdfunding. You shouldn't just be allowed to keep donating forever. We actually want to add this expiration field to fund. Now, we can't just add a field directly to the struct because fund is already this object that exists in the global storage. Maybe there are multiple fund objects. That would be a breaking change to the schema. But we can do something else, which in Sui Move, which is leveraging this dynamic field feature. So let me explain how this works via an example. So let's say we publish a new copy of crowdfunding. This is the same module as before, but it's a different version. It has the same struct declaration, but I've omitted it. And we're going to add this new function called add expiration, where it's going to add an expiration date to the fund object. So this function takes a mutable reference to a fund as input. It takes an expiration date as an integer. We've got the TX context. And what this does is, okay, it does a permission check. Not everyone should be allowed to add an expiration. Let's just pretend there's some admin who has the permission to do it. And then it calls this Sui framework built-in function called dynamic field add. And what this is doing is it takes a mutable reference to the fund's ID, and then it takes a key, which can be any type. Here, I've just used a string called expiration, and then a value where I'm just saying, okay, the expiration should be the time it is now plus whatever the expiration date. And so under the hood, what this is doing is it's going to look at the object ID, it's going to look at expiration, it'll concatenate them and hash them, and then it generates an object ID and looks up the object at that ID. Basically, this dynamic field is going to be another object that has fund as a parent and that has a key that's derived from this expiration string and from the ID of the parent. And so what that lets us do is we can go and read that field later on. So now we're still looking at version 2 of crowdfunding, and we're looking at donate, which is going to have the same signature before, but I'm going to change the body to account for this expiration. So here again, we're leveraging this dynamic field feature. What we do is we say borrow, or we have to point it again, the object ID of fund. We give it this string expiration, and then I'm saying the default that I'm going to get if expiration field isn't set is the current epoch. So what this is basically doing is it's interpreting fund as a heterogeneous object. It's kind of like a JavaScript object or something. It has static fields that I declare in the declaration of the struct type fund, but I can also add these fields on demand and then read them on demand, which is very useful for upgrades and in other contexts. And then now that I've got this expiration, I compare it against the current epoch, and then if we're before the expiration, we go through the old donate logic and allow donations, and if we're after, then we would do something else. So this is quite cool because we have the same object. We haven't changed, we didn't have to create a new object type or change the ID of the object. We have the same signature of the donate function. Clients don't have to point donate in a new thing or pass extra arguments, or their code doesn't break. There's no changes at all, but we've added this feature of expiration just by adding a dynamic field, adding an admin function that lets someone amend this object with a dynamic field, and then using the dynamic field inside of donate to add this expiration logic. So this is very useful because in the older move, I mean, these upgrades are quite painful, especially if you want to change the schema of an object. And so this doesn't quite let you change the schema of the object, but you can leverage dynamic fields to effectively do so without actually having to republish any old objects or to add a new type. So that's one example that's going into a couple of these features. I'm now going to pop up to a different layer and talk a little bit about how the Sui protocol is leveraging Move to do some of the interesting things that it does. So I'll start with a very easy one, which is this transaction data model that we have where you specify all of the input objects for a transaction, and you can talk about the effects of a transaction in terms of its output objects. Gives you a nice vocabulary to explain what a transaction is going to do or what it's done to a user, which isn't necessarily so easy to do elsewhere. In Ethereum, for example, this is a tweet from someone saying, I can't believe that you just sign transactions when you have no idea what they do. And there have certainly been lots of security issues that have been caused by this, like scams in a Discord where some scammer breaks in to say the Bored Apes Discord, and then they tell everyone sign this transaction that's doing a promotional NFT drop, and people just sign it because it came from the Bored Apes NFT Discord, but they just don't know what the transaction is going to do, and that's why the scam works. So what you can do with Sui style Move is that the transaction format enables you to do something that gives you a pretty good idea of what a transaction is going to do. I like to think of it as it enables Android or iOS style permission requests for wallets. For a transaction, you can say it can request to know what are the objects that are used and what kind of permissions do I want for each object. Do I need permission to read it, to write it, or to transfer it? So you can also get this thing by transaction simulation, of course, but this is simpler, and this is simpler to do. It's cheaper because you don't need to actually run the transaction or read any of the objects, and then it ends up being easier to explain too, I think, because you have this nice language of types and object IDs to say I'm using the object with this ID and this type and then these permissions, versus like all the crazy things you can actually do at runtime. And so in the Bored Apes giveaway scenario, if the transaction was actually doing a giveaway, all it would need to do is prove that you own the NFT. So it would ask for permission to read the cool asset, an ampersand cool asset, and then so the wallet could say to the user, "Hey, this app wants to read your cool asset. Is that okay with you?" Versus if the giveaway was malicious, and it wanted to steal the asset, it would have to ask for permission to transfer it, and then the wallet could say, this app wants permission to transfer your cool asset. Is that okay with you? And hopefully the user would say, hey, this is supposed to be a giveaway. I don't understand why I have to give away my cool asset. I should just need to prove that I own it. I think I'm not going to sign this transaction. So this, we hope, will be able to prevent a lot of these scams that basically happen due to just not having an idea what a transaction is going to do in advance. So another one is the parallel execution. So when you look at a transaction, you know the objects it's going to touch, you know their IDs, and you know your versions. And this gives you a lot of information that helps you with coming up with a good schedule for parallel execution. So basically, every transaction has these object IDs and versions. And so if you have objects with distinct IDs, they're safe to execute in parallel. You can throw them to different cores on the same machine. You can throw them to different machines. It's just a very nice upfront piece of information to help you with that kind of scheduling. If transactions touch the same object ID, they have different versions, so you know what order they need to be executed in. And so, this lets you either do parallelization on a single machine or spread out execution among multiple worker machines if you want to have a distributed validator that scales horizontally. And the other thing too is this doesn't necessarily force you to use only the static information for scheduling. Once you've used this to assign transactions to a core or a machine, you can then, if you want to, also use optimistic concurrency techniques. You have static information in the IDs and the versions, and you can also use dynamic information if you just want to execute possibly conflicting transactions in parallel to see if they actually conflict at runtime. So this just gives you a lot of leeway to do parallel execution that you don't get in other forms of Move or in other languages. And so I want to talk about another thing to do with scaling execution, which is about what we're calling object-based fee markets. So the problem that these are solving is that parallel execution is great, right? If you actually have a workload that has parallelism, but if you have a workload that has a lot of sequential contention, all of the parallel execution in the world isn't going to help you. And in practice, when we look at smart contract workloads in practice, we see the contention is very common. If you have, say, a hot NFT mint, it's usually all hitting the same contract or the same object or the same table. And so there's going to, even if you're really good at parallelism, there's just this fundamental race to see who's going to get the NFTs. So you're going to have some contention. If you're in DeFi and we're in the middle of a financial crisis and there's a liquidation, there's going to be a lot of different bots or users racing to get some high value liquidation. And there's fundamental contention. There's nothing we can do with parallel execution to make that better. And similarly, if you're trading volatile currencies, we'll all be racing to get the best price or to front run each other or do these other things that fundamentally introduce some degree of contention. And so if we're really good at parallel execution, but we don't solve this problem and we have a single gas price, then what we're going to have is a system where when there's contention in one part of the system, it spreads elsewhere. If there's only one gas price, if there's a hot NFT mint, the gas prices are going to have to go up for everyone, this so-called noisy neighbor problem. And so in Sui, we're trying to avoid this by having not a single fee market, a single gas price, but having gas prices that are based on the objects that a transaction touches. And so in Sui, this is easy for us to do because we can look at a transaction, the source of contention in Sui is easy to spot. You say, look at a transaction, see if it's touching the same shared object as a lot of other recent transactions. And if it is, basically it should be more expensive. And so the way we're working on doing this is that validators track hot shared objects for the last few blocks, basically shared objects that a lot of different transactions have touched. And we're going to set it up so that the gas price for some transaction T is going to be proportional to the hotness of the shared objects that T touches. If these are cold objects that not a lot of other people are touching, this isn't creating contention, so it'll be cheap. But if this is a hot NFT mint and a lot of other people are touching it, then it's going to be more expensive because it's going to cause contention and reduce the throughput of the system. So the property we're going for with this is that if there's a contention on shared object O, it should only affect the prices and the quality of services for transactions that are touching O. Other transactions should be unaffected, which should eliminate noisy neighbors. We don't have this nasty thing where that you get on, say, like ETH, where there's surge pricing in New York for Uber, but now it's somehow more expensive in San Francisco. Those are separate markets, and if New York and San Francisco are objects, then those should have separate prices, just like Uber would. So we're going to design this pricing scheme such that maximizing the fee revenue for validators is the same as maximizing their throughput, churning the most transactions through their cores or workers, and then so those things will be nicely aligned. So the thing I want to emphasize here is that parallel execution is great and it's very important, but it's not enough. You have to set it up so that creating contention has monetary consequences for users and programmers, and that'll align everyone's incentives to only create contention when it's really valuable and for validators to actually maximize the throughput of what they have. So the second thing I want to talk about is cheap third-party ledger verification with sparse nodes. So in a high throughput system, which is our goal with Sui, we really want to be able to handle any traffic that consumer and enterprise use cases throw at us. We don't want to have some bottleneck where, the system runs out of throughput once you reach the limits of this machine. We want to be able to scale the way systems in Web2 do, add more commodity machines, and then we get more throughput and we get more storage. So, and this is within the walls of a single validator. And so we think that any high throughput system is fundamentally going to require beefier validator hardware and more storage. But what we don't want is for full nodes to also be correspondingly expensive. I think it's okay if validators need to use more resources because this is somewhat fundamental, but if you have a lot of really cheap full nodes, then that matters less because then anybody can still check the work of the validators and make sure that they're being honest. Basically, we really want the barrier to entry for third-party ledger verification to always be as low as possible. So with the Sui transaction model, there's also an opportunity to do this better with this. Instead of having a full node, we can have a so-called sparse node. And what a sparse node does is it only tracks state and transactions that are relevant to some set of causal roots. This might be a set of addresses, a set of objects, or a mix of these things. So Maybe for a wallet, you're a sparse node that only tracks the objects that are owned by that wallet's addresses. If you're someone who creates a game, maybe you only track the addresses and objects that are involved in that game, but not the rest of things. And basically what you can do is, because you're only tracking the subset of things, you can look at transactions in advance and you can see what objects does it touch, and you can only subscribe to those transactions and replay those transactions. And so the algorithm is quite simple. You watch for transactions that touch the objects that you care about. You fetch the that touch the object IDs you care about. You fetch the actual objects behind those IDs, and then you replay the transactions. And so the nice thing about sparse nodes is that, unlike a full node where the cost of running is proportional to the number of transactions in the system, the sparse verification cost is proportional to the number of relevant transactions to the objects you care about. So basically, if you care about a lot of things, it'll be more expensive. If you care about a few, it'll be less expensive. But in practice, we think if you have a sparse node that cares about a reasonable number of things, say like a wallet, it should be very practical to run on a phone, to run on a laptop, just as long as the number of things you care about isn't too many. This is quite practical to do compared to the system as a whole, which may be pushing hundreds of thousands or millions of transactions per second. So these are the conclusion of the topics I had to talk about today. I talked to you about how Sui is leveraging Move and this how it has this object-centric data model that gets used in a number of ways, a more direct Move programming style compared to DM style Move. These safer wallets via transaction permissions that are enabled by that data model, maximizing parallelism with I actually didn't talk about that one, but happy to talk about it some other time. Scaling throughput and storage with parallel execution and intra-validator sharding, discouraging contention with these object-based fee markets, and finally, enabling cheaper third-party ledger verification with these sparse nodes. Include a number of links, which folks here probably know about, to the Move language and the awesome Move content aggregator, and to the Sui GitHub, to our docs, and to the Explorer for our DevNet, which I encourage folks to play with if you haven't tried it out and are curious to check out this flavor of Move. Thank you again for inviting me. It's a real pleasure to be here, and very happy to take your questions.